Hi and welcome. My name is Rosemary Guzman and my research is in low-dimensional topology and geometric theory. Thank you to our dear organizers, Bianca, Alex, Mario, for the invitation, and also thank you to you for joining today. So the title of my talk is Introduction to Hyperbolic Manifolds and Quantitative Mostow Rigidity. And the goal is to get acquainted with hyperbolic geometry and sort of develop an appreciation for what makes the study of hyperbolic manifolds interesting and rich. Okay, so let's get started. So two words you'll hear a lot in today's talk are geometry and topology. Okay? So geometry is concerned with lengths and angles. So from the point of view of geometry, these are not the same. They are not isometric. Okay? And topology is concerned with continuous deformations. Okay? So the question is, can I continuously deform any one of these into any one of the others? And the answer is yes. Okay, so to be more concrete, I can construct a map which is continuous and is a bijection and has continuous inverse between any two of these objects. Okay, that's called a homeomorphism. So again, a map, topological spaces, which is continuous, is a continuous bijection with continuous inverse. It's called a homeomorphism. So these are all homeomorphic. And when I know two topological spaces are homeomorphic, I know that they share what are called topological invariants. So topological invariants are topological properties that are preserved under homeomorphism. So if I have a topological space X and I know it's homeomorphic to a topological space Y, and I know some topological invariant of X, it must be also a topological invariant of Y. And in fact, here, all of these can just be continuously deformed to a point. And we would call that contractible. Okay? So they all share that property. And that's a property of the fundamental group of a space, which is something that we'll talk about today. A fundamental group is a topological invariant. Okay, so the theme for today is the interplay between groups, abstract algebra, topology, and geometry. Okay? And the groups that we'll be looking at are symmetries. Okay? So here, gamma is a subgroup of the isometry group of hyperbolic space. Okay? So isometries are just distance preserving maps, right? So they're the symmetries that preserve distance. So you're familiar with the isometries of the Euclidean plane, right? We have rotations, translations, reflections. Except today we won't be considering reflections, right? Those are orientation reversing, and we're going to be looking at manifolds which are orientable. In other words, we don't want to have reflections in our isometry group. Okay, so we'll be looking at the orientation preserving ones. Now, what do we do with these groups? Okay, so we construct hyperbolic manifolds from them. Okay, this is exactly how we do it. So if you take hyperbolic space and you quotient out by, it looks like you're saying you're quotienting out by gamma, but we write that to mean that we're quotienting out by the action of gamma, okay, on hyperbolic space. So this is how I make my this is how I, cook up my hyperbolic manifolds. This is exactly how. So what does it mean then to have hyperbolic space and quotient out by the action of an isometry group? Okay, what it means is that, all right, well, so if I take a point in hyperbolic space, let's call it X, then I want to look at all of the points gamma X, right? Gamma is just my group of isometries here. So I look and see where gamma takes X, okay? So I get a whole bunch of points, right? Wherever gamma takes X, that's the orbit of my point X, okay? So all of those points are called those points, gamma X, are the orbit. That's the orbit of X. And I'm going to be thinking about that as one thing because this is a quotient space. That's my equivalence class. So in other words, if gamma takes x to y, then I think about x and y as the same. Okay, so I'm modding out by identifying points under the action of the isometry group. Okay, so groups and the geometric objects they act on. Okay, so if a group acts as symmetries of a geometric object, then we can use the geometry of that space to inform our understanding of the group. It's a way of having sort of a geometric representation of the group, okay? Which maybe you had only described algebraically. Now, it's a fact that every group is a set of symmetries of some geometric object, okay? So we can take something called its Cayley graph. So you have at least one geometric object that every group acts on. It's Cayley graph, okay? And the Cayley graph of a group is just, contains as vertices all of the elements of the group. And edges are labeled with generators. Now, it may be ugly, but we always at least have that. Okay, so take a look at this group, right? This is the dihedral group. Now we have the algebraic representation here of the dihedral group, right? We have two generators and we have some relations. But when we see them as the group of symmetries of the square, we now have a geometric understanding of the group that we didn't have before, right? So our rotation, right? So if I rotate 4 times, or if I flip and flip again, both of those operations take me back to where I started, right? And so they're the identity. We also have another relation there, which is that if we rotate and flip, that's the same as flipping and rotating in the other direction. Okay, so our next example is Z cross Z, or Z2. So it has two generators, A and B, and they commute. This is abelian. So AB equals BA, and on the right, you'll see I'm looking at the action, right? One way to think about this, I want to look at the action of this group on R2. So you can see, for example, that it preserves the lattice structure of R2. So for instance, points with integer coordinates are all taken to points with integer coordinates, for example. And in particular, right, if I do A and then B, so you can see, let's say we're at the unit square. So let's start at 0, 0. So if I apply A, then, and if I then do B, I get to 1, 1, and that's the same as first doing B and then A, okay? So now another question to consider is, since we just learned about topological spaces and quotienting out by group actions, what would it look like if I took R2 and I quotient out by the action of Z2? Okay, so I have R2 and I want to quotient out by the action of Z2. Now remember, that means that within a given orbit, so if I have a point, all points within, so all points corresponding to the orbit of that point, they're all identified. So for example, if we look at the unit square, let's say we take the center point of that square, then I can apply A and B in any way, in any order, in any number of times I want, and I'll always get to another center point of another square, right? And so all of the center points of squares then are identified, for example, right? So we can think about every point in the unit square this way. And so if I take R2 and I quotient out by the action of Z2, right? Then what I'm left with then, for instance, would just be, one example is just the unit square. And with the edges identified corresponding to the generators. Okay, so again, today's groups are hyperbolic 3-manifold groups. So these are the isometry groups of hyperbolic 3 space. And one thing we want to do today is try to take some quantitative information away about hyperbolic 3-manifold groups. And that should trigger your mind into thinking about geometry, and that's right. But as mentioned, we have more to discover about how the geometry will interact with, let's say, topology of the manifold. Okay, so Okay, in the beginning, there were the elements, right? Circa 300 BC. And this was the definitive work on geometry, and well-deserved, for over 2,000 years. And mathematicians spent a lot of time trying to prove the parallel postulate from the other four postulates. But it wasn't possible. It was impossible, and for good reason. Okay, so Gauss discovered around 1830 that if we actually remove the parallel postulate and just retain the other four, we can develop a consistent geometry, a non-Euclidean geometry. Now, Gauss never published his work, and shortly after, Lobachevsky and Bolyai also independently discovered hyperbolic geometry. So let's recall the parallel postulate. If I have a line and a point not on that line, then there's exactly one line through the point which doesn't intersect the original line. Now, if I remove that criteria, that opens the door to new kinds of geometry, such as hyperbolic geometry. Okay, so if I have a line and a point not on that line, there are infinitely many lines through the point that don't intersect my original line. Or spherical geometry. So if I have a line and a point not on that line, there are no lines through the point which don't intersect the original line. In other words, all lines must intersect. So there is no notion of parallelism there. Okay, so to get an understanding of hyperbolic space, we want to choose a model. We want to look at the geodesics and look at the triangles. And what are the geodesics? Those are just the distance minimizing curves. So if I have 2 points in my space, what's the shortest way? What's the shortest distance between them? It lies along a geodesic. Okay. So what's the shortest distance between them? It's a geodesic. The geodesic has to be in my space. Okay. We know what that is for the Euclidean plane, right? If I have 2 points, we join them by a line segment if we want to get there in the shortest, along the shortest distance. Okay, so this is just recapping the notions of parallelism or non-parallelism that we talked about on the other slide. Okay, so with some other pictures here. And of course, on the left, that's the Euclidean plane. And in the middle, we can see that this is like a sphere. And then the third is like a saddle. So this is hyperbolic. Okay, so models of the hyperbolic plane. There are other models of the hyperbolic plane, like the hyperboloid model and the Klein model, but we want to stick with models that are conformal, okay? In other words, models that preserve angles. So here we have 2 conformal models of the hyperbolic plane, the Poincare disk and the upper half space model, and how do we get them? So what are they? All right, so to clarify, in each of the models, the way we construct is by looking at the underlying space for each model, and we take that together with the boundary. Okay, so in each of the models, the underlying space and boundary are different. So let's look at the Poincare disk. So that's the set of imaginary numbers with modulus less than 1. In other words, the unit disk in the complex plane. It has as its boundary the unit circle. Okay, sometimes we call that S infinity. And the upper half space model has as its underlying set the imaginary numbers with positive imaginary part. That should say imaginary part of z greater than 0 instead of 1. So positive imaginary part. And the upper half space has as its boundary the real line union in a point at infinity. And you can see in the model below, so that's literally a point at infinity. Okay, so that is a point on the boundary of the upper half space, right? So a real number line and a point at infinity. And that's the boundary. So when I take that together with the underlying space, the imaginary numbers with positive imaginary part, I have a model for the upper half space, right? I have to specify what the geodesics are for each now, right? So in the upper half space, the geodesics, in other words, the distance minimizing curves, those are Euclidean circle arcs, which are perpendicular to the boundary, okay, or vertical lines, okay? Euclidean vertical lines and Euclidean circle arcs, both of which are perpendicular to the boundary. Okay, so those are our lines in the upper half space model. And you can see some drawn there, right? So the when we say circle arcs orthogonal to the boundary, they also have by default the centers of those circles lie on the boundary, so lie on the real line. Now going back to the Poincare disk model, the geodesics are also circle arcs perpendicular to the boundary, right? Or diameters, okay? Okay, so what this means is like in the Poincare disk model, we see that if I have 2 points, so they're in blue, and I want to find the shortest path between them, I have to actually go along the green segment. That lies on that's what lies on my line. It lies on a circle arc, and those are the which is perpendicular to the boundary in that model. And those are the geodesics. Those are the lines. So sorry, those are the lines. And so my geodesic, my shortest path, is in green. Okay, so it wouldn't be the Euclidean line segment joining them. That would actually be longer. Okay, in terms of the distance of the metric that's on this space. Okay, and on the right in the upper half space model, you can see, I don't know if you can see in yellow, I also had 2 points, and the geodesic, the geodesic between them lies on the line. What is the line? It's that circle arc there that's orthogonal to the real axis, which is the boundary of upper half space. And so you would just you would travel along. Oh, that is not good. You would travel along that path if you wanted to take the shortest path between the 2 yellow points. Okay, so ideal triangles in H2, the hyperbolic plane. That's one kind of triangle we can look at. What does that mean? What does ideal mean? It means that at least one of the vertices lies on the boundary of the space, okay? And here in each of these examples, for whatever model we're looking at, we have all vertices lying on the boundary of that respective model. So on the left, you see the Poincare disk, and I tried to highlight the geodesics for each of these triangles so that you could see, again, those are all circle arcs perpendicular to the boundary, okay? And in the upper half space, so it's a little bit more wacky, maybe, to try to figure out and understand that these shaded regions are indeed triangles here. Okay, so on the upper half space model on the left, in blue, that's one side of the triangle, in green is another side, and in red, that's another side. It's an ideal triangle. All of its vertices are on the boundary. And on the right, we have another triangle, right? And in black, you can see each of its sides. Okay, so the vertical lines, right, that are orthogonal to the real axis, those are lines in the hyperbolic plane. So that's, and where do they go? They actually join at the point of infinity. So this is indeed, they join at the point of infinity. So we have a triangle here, an ideal one, but still a triangle. Okay, so what can ideal triangles do? Let's watch them tile the hyperbolic plane with Mona Lisa inside because it's fun. And this app is on Malin Christensen's website, and I give the link in the last slide of the animation. So here we go. So this is a tiling of the hyperbolic plane in the Poincare disk model. And so what that means is that all of these triangles here are the same. The blue triangle is the same as the red triangle, is the same as every other triangle that you see here. And what you start to get a feeling for is that as we get closer to the boundary of the hyperbolic plane, right here in the Poincare disk model, or even in the upper half space model, you start to get a feel that things blow up, right? So you can imagine that maybe there are lots of hills and valleys or something like this, if you want to have sort of a picture in mind, maybe like, very curly, like a kale leaf. Near the boundary, and getting even more curly as we get closer to the boundary. Now, it wouldn't be right if we went on and didn't tile the hyperbolic plane again with another beautiful image, but this time our tile is a triangle, which is not ideal. Okay, it's just an equilateral triangle. And again, this was using Malin Christensen's app. And you can see the hyperbolic lines, right, in the radius model. So they're in gray. They're diameters and Euclidean circle arcs orthogonal to the boundary here, which is just S1. Okay. So here, let's look at a vertex. So there are 7 triangles meeting at a vertex. So each has angle 2 pi over 7. Now, due to Gauss, we know that the area of a hyperbolic triangle is its defect. In other words, pi minus the sum of the angles. Okay, so the sum of the angles here, we have 3 angles so for a given triangle, we have 3 angles of measure 2 pi over 7. So pi minus 6 pi over 7 is pi over 7. So the area of each of these triangles is pi over 7. Now, what should stand out right now to you is that we were able to compute the area of this triangle using the sum of the angles. Now imagine in Euclidean space, knowing the angles of a triangle does not tell us sort of what the area is going to be, right? We can scale, we have similarity transfer, we have similar triangles in Euclidean space. Now, the area formula can be deduced from the Gauss-Bonnet theorem, okay, which we're not presenting here, but another cool fact is that if you have a triangle with angles pi over a, pi over b, and pi over c, and the sum 1 over a plus 1 over b plus 1 over c, if that's less than 1, the triangle is hyperbolic, equal 1, it's Euclidean, greater than 1, it's spherical. Okay, that also can be deduced from the Gauss-Bonnet theorem. And so we get this fact that there exist equilateral triangles with any angle greater than 0, less than pi over 3. And so we have an infinity of tessellations by equilateral triangles, right? Juxtapose this with the Euclidean case where we have exactly 1 tiling of the plane via triangles, right? Equilateral triangles. So before we go on, I sort of hinted at the notion of length earlier. We talked about geodesics as distance minimizing curves. But I didn't really give you a notion of distance, okay? So we wanted to find a metric. A metric is sort of what's going to tell me, oh, what's the distance between 2 points in the space? And we define that as the infimum of the lengths of all paths joining my 2 points. And in the upper half plane, here is how we define length. It doesn't come from nowhere. I mean, it's related to a Riemannian metric, but so the path here, FAB, goes into the upper half plane. If it's parameterized, let's say x of t plus I times y of t, right? So the real part's x of t, the imaginary part is y of t. Then in the integrand there, I get 1 over y of t. And then dz is just like the Euclidean arc length element, okay? So it's going to be the square root of x prime of t quantity squared plus y prime of t quantity squared. And I give you an example here to think on a little bit, that if I have 2 points on the imaginary line, AI and BI, in the upper half plane model, you see that the length, at least here, in terms of this parameterization, would be as given. Now, it turns out that the parameterization doesn't matter, and that that infimum is actually realized in this space. So there's a lot of things here, but the point is, I can come up with a notion of distance. Now, we've seen that hyperbolic geometry is more rigid than Euclidean geometry, right? We saw the area of a hyperbolic triangle is given as pi minus the sum of the angles, right? And so again, and I mentioned we should have pause on there, think about this again, 2 triangles, equal angles, the triangles must be the same. Okay, so unlike Euclidean triangles, 2 hyperbolic triangles with the same angles are isometric. Isometric. And think about how startling that is. If I said to you, think about the 30, 60, 90 triangle. I wouldn't know exactly which 30, 60, 90 triangle you're thinking about. Okay, so when you juxtapose that, the point is when you juxtapose this with what's true in the Euclidean case, it's pretty surprising. Okay, so in other words, in hyperbolic space, you can kind of have this idea that the shape of a configuration determines its size. So I know the angles of a triangle, I know the triangle. And a little bit of fun before we go on. This is an example of hyperbolic crochet taken from Dana Tamina's page. And if you think about it as a hyperbolic disc and you sort of superimpose it with the center of this with the center of the Poincare disc, then you sort of get an idea of what's going on as we start at the center, the origin, and we start heading toward the boundary, right? Things get big really fast. And you would be right to posit that. In fact, area grows exponentially with radius in the hyperbolic case. So does circumference, also grows exponentially with radius. But look at that, you can see all those curls and trails of, so it's not that surprising. But when you compare with the Euclidean case, circumference is linear with radius, area, in the case of area, it's quadratic with radius, right, pi r squared. So, wow, really different to think that these quantities grow of area circumference, they grow exponentially with r. And when you see this, it kind of feels not surprising. And this comment below on how would we play a comparable game in hyperbolic space is due to a fun number file video by Dick Kaderi, so I encourage you to watch it. Next, on to getting to know hyperbolic manifolds. All right, so introduction to surfaces, two-dimensional manifolds. So when you hear surface, that's a manifold in dimension 2. Now, in the first content slide, we essentially gave the definition of a hyperbolic three-manifold, and it's not much different here for two manifolds, whether hyperbolic, Euclidean, or spherical, right? So we get the manifold, and you can see in the second, in the bottom box, it's gotten by taking the respective space and quotienting out by a group of isometries, okay? And just like in the case of hyperbolic three manifolds, but here the isometry group is, would be an isometry group corresponding space. Okay, and in this construction, we get that gamma is isomorphic to the fundamental group of the manifold. And we're going to see an example of the fundamental group on the next slide. We're going to look at the torus. So we're definitely going to come back, by the way, to this idea that gamma and its fundamental group are isomorphic via our construction here, but quotienting out by the group of isometries. But for now, let's try to get our hands on what the fundamental group kind of means. So one technique we use to find the fundamental group of a surface is that of identification spaces. Okay, so these are polygons with edge labels, and you see here we have a square. So we have the red edges, you see we identify them, so we glue them together, see that below the square. Then to the right of that, you see we're going to identify the green edges, and then the result is above, which is the torus. That's the final result. And we can see then we have two loops, the red, one associated to the red, one is and the green loop. So we have the red loop, the green loop. What does this mean? So it turns out that these are the generators for the fundamental group of the torus. Okay, red, that's the A. You'll see there's a I gave pi 1 of t. That's the fundamental group of the torus. A comma B, and it's such that AB equals BA. Okay, so this is Z cross C. We saw this earlier in the talk. Okay, and so what does it mean? So if I look at a loop on the torus, okay, at a point, and if I look at a loop and I can really then transport it in a continuous way into one of these loops or some combination of these loops, okay? Now, if in general, if I want to say something a little more formal, for a topological space, the fundamental group is, let's say it's connected, then the space is connected, then I would look at a point in the space and I would consider the loops at that point, and I would think about, well, if I can continuously take that loop, if there's a family of continuous functions that take that loop to another loop, then those loops are in the same equivalence class of the fundamental group. Okay, so the fundamental group is just a group of equivalence classes identified that way, which is via homotopy. All right, so so here, yeah, so pi 1 of the fundamental, pi 1 of the torus is Z cross C. And you can use this technique for other surfaces you might be familiar with. The technique is the same. So we have a surface, pi one of it has as relations the closed path read off from the single vertex of the identification space with polygon edge labels as generators, right? So we always end up with a single vertex after the identification. All right, so I'm not going to go into detail about this. What you see in the picture there is a wedge of two circles. It has fundamental group, the free group on two letters. We also saw that earlier in the talk. And the free group on two letters just is all of the vertices that you see of the Cayley graph there. So for instance, AB, BA, ABA, free groups don't have relations. So we can't reduce those anymore. All right, so all of this work was to think about the following. So we have here, we looked at the torus, that's the genus 1 surface. This is a genus 2 surface. We actually take a connected sum of tori, so it's a way of putting them together. It actually can't be modeled by R2 the way the torus was. And we saw earlier in the talk that R2, right, this square here, that we were able to model, the torus on R2, okay? That was in the second content slide. All right, now this surface can be modeled. It can't be modeled in the by R2, but it can by on the hyperbolic plane. Okay, and so you can see here some kind of picture explaining that. This is just the regular octagon tessellation of H2. So again, the genus 2 surface, which has the octagon with certain edge labels there, can be modeled by the hyperbolic plane. It's really interesting. Now, this leads us to the classification of surfaces. These are two-dimensional manifolds. I'm only looking at closed, connected, orientable ones. So for closed, connected, orientable surfaces, it's pretty amazing. This is it. This is everything. We either have a sphere, we have a torus, or a connected sum of tori. So any number of tori. So I only show up to the genus 2 surface, but we can connect another torus, we get the genus 3 surface, and so on, okay? And so the takeaway, right, and then genus 4 surface, genus 5 surface, and on and on and on. The takeaway is that for in genus, we just say kind of the number of, so you think about it, well, it's the number of handles attached to a sphere, just, you think about these holes here. Most surfaces are hyperbolic because if I consider all surfaces of genus greater than or equal to 2, they are hyperbolic. If they're closed, connected, orientable. The only non-hyperbolic closed, connected, orientable surfaces are the sphere and the torus. So it's pretty amazing. There are infinitely many hyperbolic manifolds in dimension 2, so surfaces. And there are only finitely many non-hyperbolic ones, okay? All right, so a note here about the Euler characteristic. It's a topological invariant. It's something you probably have seen before. So thought maybe nice to draw into something you might be familiar with. You may have computed it for a polygon or some sort of platonic solid, the vertices minus edges plus faces. And what's really cool is that we can compute the Euler characteristic for genus 2 surface using the identification space with the, so you see here we have this, these are the relations, the pair of edges and vertices are identified. We get one vertex, 2 G edges, and 1 face. And so we get that the Euler characteristic of a genus G surface is 2 minus 2G, using the same idea. Okay, and yeah, so we can generalize the idea of Euler characteristic anyway for other n-manifolds. It's alternating self-repeating numbers, so it's just really cool. It has generalization. All right, so now so anyway, all of this is to say is that the Euler characteristic, which seems very geometric in nature, vertices, edges, faces, has an expression. So we have this Euler characteristic. It's a topological invariant. Okay, so this is already a sense of wow. So we're really seeing a connection here then between geometry and topology, and the Euler characteristic does that, and we haven't even gotten to 3 manifolds. Okay, so back to let's talk about isometries. Okay, so the orientation preserving isometry group of hyperbolic n space, isom plus hn, that's how we denote it. Okay, so we're going to think of H2 being modeled by the upper half plane here. So you'll see here first, so what are the orientation preserving isometries of the upper half plane? So we talked about the need, how important it is to get a sense of understanding the isometries of hyperbolic space, because the action of them on hyperbolic space forms the quotient that gives us our manifolds. So it turns out that if we're looking at the upper half plane model, the isometries can be modeled by the projective special linear group with real coefficients. So these are actually the Mobius these are the Mobius transformations that preserve the upper half plane if you've taken complex analysis before, AZ plus B over CZ plus D. Okay, so we have a matrix here, A, B, C, D. It's in PSL2R. So those are just the matrices. So this is PSL2R is a subgroup of the general linear group, right, which has matrices of non-zero determinant, therefore invertible. And SL2R are the matrices with determinant 1. Okay, and we're modding out by the center. So we're looking at modding out by plus or minus the identity. And so every isometry in the hyperbolic plane can be expressed as AZ plus B over CZ plus D, and we associate with this, so the corresponding matrix in PSL2R. And so the isometry group and PSL2R are isomorphic like this. And we can do the same for H3. So except in this case, the matrices have complex coefficients. So it's a little bit more tricky. All right. So again, why do we care about isometries and how they act on hyperbolic space? Well, because we remember how we construct manifolds. It's the space quotient by the action of the isometry. And what you see here is, so it's a loxodromic isometry. So isometries, it turns out, so I'll go back here, they're AZ plus B over CZ plus D. If you look at the fixed points, right, so when that equals Z, those classify the isometry. So a loxodromic isometry has two fixed points in the boundary. You can see that. And what you see here along the lines are sort of the motion of points. Okay. And I might refer back to this later on. These are, you can also see in the picture why these are called banana isometries. So anyway, there's a sort of a central axis and the points are moving along sort of being translated and twisted a bit as they go. Okay, I'm going to summarize this slide by saying that the action of gamma, a subgroup of the isometry group H3. So we're looking at discrete groups, which means that for a point X in hyperbolic space and given my group gamma, that if I look at the images of X under gamma, that set of points is a discrete set. So that's one way you can understand that the action is nice, okay? And here we are, intro to hyperbolic 3 manifolds. Okay, so all I'll say about this slide is that these are the extension of, here the Poincare-Bolle model is the extension of the Poincare-Diss model. So of course, the Poincare-Bolle model is a model in higher dimensional hyperbolic space. Same thing with the upper half space model, right? This is a generalization of what we saw in dimension 2. Okay, so now it's still true that the geodesics in both models are circles orthogonal to S infinity. Okay, and there's a little game down here. Go rogue if you want to see what it's like to play a game in hyperbolic space. So this is really cool. Give it a try and let me know how it goes. All right, 3 manifolds. Okay, so if you haven't guessed already, H3 exists. I think we've established that. And the important thing here, the geometrization theorem. So conjectured by Thurston and resolved by Perlman recently in 2003 is that every closed 3 manifold can be canonically decomposed into geometric pieces, each having one of the 8 model geometries that's shown here. Okay, so In dimension 2, we had the classification theorem of surfaces. Okay, in dimension 3, it's more complicated, right? So we have for closed connected orientable surfaces. So in dimension 3, it's more complicated. These 8 model geometries, some of them are formidable, I will tell you, but you're familiar with some of them. Look, we have E3, that's the three-dimensional Euclidean space, that's S3, three-sphere, H3, hyperbolic space, S2 cross R. So you know some of these, but what's notable is that just like in the case of surfaces, most closed 3 manifolds, right? So surfaces are 2 manifolds, most are hyperbolic. And I will leave that in quotes. All right, so hyperbolic manifolds, we've also already gone over this one. The important thing to remember is that when I take, so I'm extending this from the dimension 3, n equals 3 to all dimensions n, right? So it's the same. We construct n-dimensional hyperbolic manifolds, or Euclidean or spherical, by quotienting out by a group of isometries. Okay, and again, reminder that gamma is isomorphic to the fundamental group of the manifold, a basic topological invariant, when via this construction. And alternatively, too, every hyperbolic 3 manifold that we have, or hyperbolic n manifold, is gotten about via this construction. Okay, must have been constructed this way. And just for fun, hyperbolic dodecahedron, really cool. Okay. Okay, a recent result of Ian Nagel 2015. So what you see here, it's a big result in 3 manifolds. Why is it big? Because Ian Nagel won the $3 million breakthrough prize. So you might agree. It's a result about hyperbolic 3 manifolds, or more general class of 3 manifolds, certain class of manifolds, 3 manifolds with an infinite fundamental group, it was the virtual fibrine conjecture, and it was big news to have a mathematical result, notably result in 3 manifolds recognized in that way. So now we're going to talk about Mostow rigidity. In dimension 2, there are many non-isometric flat tori. So tori are not rigid objects. We can deform, rescale. So Mostow rigidity, which we have yet to define, you will see later how this is a shadow of Mostow rigidity. We saw this in dimension 2 when we talked about shape determines size, shape determines size. So the hyperbolic surfaces, dimension 2 manifolds, they seem to have some aspects of rigidity, but they're not completely rigid, okay? And so in fact, for the genus G, so for we can endow the genus G surface with many non-isometric hyperbolic metrics. So in the case of dimension 3, what's true is that unlike surfaces, 3-dimensional hyperbolic manifolds cannot be deformed. Well, I mean, the closed ones, okay? So again, we've seen, so before we unpack this, rigidity is something we've had a little bit of exposure to. The Gauss-Bonnet theorem formula for the area of a hyperbolic triangle, the area of a genus G surface. You know, we've seen some instances of shape determines size, right? And so again, that involved the Euler characteristic, right, which is a topological invariant, but it was related to something geometric. So again, geometry, topology, and this is sort of the big culmination of the relationship between geometry and topology. One of them, it's given that we have 2 closed orientable hyperbolic 3 manifolds. If they're homotopy equivalent, then equivalence is actually homotopic to an isometry. And in terms of what we've talked about today, I mean, we can explain this in saying that, well, if 2 manifolds are homotopy equivalent, they have the same fundamental group, and that means that the 2 manifolds are isometric. Okay, so very different from the slide where we had topology, geometry, and topology slides in terms of the Euclidean space. I mean, in hyperbolic space, if two manifolds are homotopy equivalent, they are the same, okay? We didn't see that at the beginning of the talk, okay? They're isometric, okay? That's really important. They're isometric. So that's like, if we looked at the slides from the very beginning of the talk, that would be like saying if I know the, this is saying that, well, when I know the topology, topological classification of certain types of manifolds, then is equivalent to classifying them up to isometry. So this is, so that's called Mostow rigidity, okay? It's one consequence, an important one, is that something which seems not topological, volume of M, it's geometric, it's geometry, it's a topological invariant, okay? All right, so again, so a pi 1 of M, as we see here when we unpack this, if the manifolds have isomorphic fundamental groups, they're isometric. So topology determines geometry. Okay, so the fundamental group completely determines the geometry of M, is what it's saying. Okay, so volume is a topological invariant. Okay, so it's powerful. I mean, we know some things about the set of volumes. We know that they're a well-ordered subset of R, the ordinal type omega to omega, that's just Thurston, Jorgens, and Rowoff. And we know that in dimensions greater than 3, there are most finitely many hyperbolic manifolds up to isometry of a given volume. Another cool result is that because of this, we can have a smallest volume hyperbolic, closed hyperbolic 3 manifold, and that's the Weeks manifold. Okay, and that has volume 0.9427. Okay, so what are some takeaways? That closed hyperbolic 3 manifolds are completely determined by their fundamental group in dimensions greater than or equal to 3. Hyperbolic 3 manifolds are very rigid objects. And for hyperbolic manifold, the geometry interfaces with topology in a way we've never seen before. In fact, the topology determines the geometry, and we get certain things which we think about related to geometry, like volume, that they become topological invariants. So again, the theme is that shape determines size, some kind of overall way of summarizing it in hyperbolic space. You know the shape, you know the size, and the shape, that the objects are somewhat very much determined the geometry by the topological properties. Okay, so what is quantitative Mostow rigidity? So the aim of quantitative Mostow rigidity is to extract concrete quantitative info about the geometry of a closed hyperbolic 3 manifold from its topological data, right, especially the fundamental group. And again, the top bullet from our volume page is a reminder of why that's so useful. The fundamental group, because of Mostow rigidity, completely determines the geometry of M in a sense, right? So in principle, we should be able to read off geometric invariants like the diameter, the volume, the length of the shortest closed geodesic, etc., just from a presentation of the fundamental group, in principle. Now back to quantitative Mostow rigidity. So what we're going to do, we impose natural group theoretic conditions on the fundamental group, and that's how we get our geometric data. And that condition is called K-freeness. We'll look at some examples of quantitative Mostow rigidity, and this will lead us back to the question of what does this imply about the volume of M? Okay, so this geometric invariant. All right, so now again, we have our construction. M is closed orientable hyperbolic 3 manifold. So we get it via hyperbolic 3 space quotient by the action of a discrete torsion-free subgroup of isometries of the orientation preserving isometry group, right? Gamma is isomorphic to pi 1 of M via our construction. So this was a seminal result in quantitative Mostow rigidity. It's called the log 2k minus 1 theorem, and it's due to Anderson, Canary, Peter Shalen, and Eagle, Caligari, Gadby. What the statement says, so we're going to think of the group below as a subgroup of gamma. That's how we're going to apply it. So if we're given these purely loxodromic isometries, which freely generate a discrete group of rank k, then the idea is that a point in hyperbolic space has to be, at least one has to be moved by a distance greater than or equal to log 2k minus 1 for this inequality to be satisfied. So, okay, before moving on, I think it's helpful to absorb the import of this result by looking at a special case, maybe when k equals 2. All right, so it says that if we have two isometries, C1, C2, which are loxodromic, and they freely generate a discrete subgroup of the isometry orientation preserving isometry group, in this case of rank 2, we're assuming k is 2. So I have two such isometries, loxodromic isometries, the kind we've seen already in the previous slides, right? These these are the isometries that move points sort of along some sort of line invariant under an element of gamma. And it's like they act as translation along some line, which is invariant under an element of gamma. And what this is saying is that, so if I've got two such isometries, they generate a group of rank 2, then at least one of them has to displace any point you pick in hyperbolic space, at least one of the pair has to displace a point by distance greater than or equal to log 2 times 2 minus 1, so that's log 3, greater than or equal to log 3. So again, two such isometries, they freely generate a group of rank 2, so basically one is not power of the other. Then if you take any point at all in hyperbolic 3 space, then at least one of those isometries has to move a point by a distance greater than or equal to log 3. And this is true for choose any point in H3, choose any such pair of isometries. So it's really interesting. We have some algebraic statement, right? We're talking about the rank of a certain group, a subgroup of isometries, and we're able to get very strong geometric information about how they move points in hyperbolic space. And of course, we're going to translate that into some information about the manifold, which is just the hyperbolic space that we can quotient out, let's say, by the action of this the subgroup of isometries. And so you see that in the center box. So one thing we could say, instead of saying something about the isometry group, is the log 2k minus 1 theorem of Anderson, Canary, Color, Shalen, Avo, Carey, and Calvi says here, in terms, stated in terms of isometries. We can reword it to say something in terms of the closed orientable hyperbolic 3 manifold. So to make the statement, though, we need a definition that's above. So a group is K free if every finitely generated subgroup of that group of rank less than or equal to K is free. Okay. So if my group is 5 free and I have a finitely generated subgroup of rank 3, then that subgroup is free. Okay. So all right, going back to the center box. So if we have a closed orientable hyperbolic 3 manifold with K free fundamental group, then there's a closed geodesic of the manifold of length at least above 2k minus 1. Okay. All right. So remember, there's, this interplay, it keeps going on, right? Geometry, topology, and this extension here that I have it's related to. So if you look back at the log 2k minus 1 theorem, you can think about the case k equals 2 again, right? And so in that case, right, let's say I have again isometries xc1, xc2. They generate a free, they freely generate a group of rank 2. All right, so then I can think about C1, C2, and C1 inverse, C2 inverse, right? So those are 4 isometries, and I can think about all the ways to combine them. Remember, these are not abelian. Okay, so there's 12 different ways. So I'm calling those like length 2. So in other words, composing one isometry with the other, C1 and C2 inverse, or C2 inverse and C1. So that I'm calling a length 2 word. And what's true is that at least for the length 2 words, right? So the log 2 k minus 1 theorem says something about how a single isometry with the given conditions displaces a point. So this extension just says something about how a composition of 2 isometries with the given criteria displace a point in hyperbolic space. So at least we get that there's a closed geodesic in the manifold of length at least log 5, for instance. Okay, so for this quantitative Mostow rigidity result, we need to know what a hyperbolic cylinder is. So Z sub log 2k minus 1 there. Okay, so we have this slide that defines it. Right? So defining things takes work, but instead we can use our picture of the banana that we have from before. Okay, so this is a hyperbolic cylinder. Okay, so it's the set of points in hyperbolic space, all moved by a distance less than something. Here we're using log 2k minus 1 because truly this results a corollary of that theorem. Okay, so this is a hyperbolic cylinder set of points, all moved a distance less than log 2k minus 1 by some isometry. We'll say xc1 in gamma. Okay, and so xc1 acts like translation along an invariant line, which is like the xc1 invariant line, which is in the core of this banana. Okay, all right, so there's my hyperbolic cylinder, and imagine that I have another such hyperbolic cylinder, another banana. Okay, so and maybe the generating isometry that is xc2. Okay, so again, we're going to look at all the points that xc2 moves by distance less than log 2k minus 1. And we'll do the same for, let's say, in another isometry, we'll see c3, c4, whatever. Now, no matter how many of them I have, let's say I have n of them that intersect. Okay, n intersecting bananas. I mean, I don't know how many. Okay, but no matter how many of them I have that have non-empty intersection, okay, what's true is that the rank of the group that's generated by their by their generating isometries cannot be too large. No matter how many intersecting bananas I have, the corresponding generating isometries cannot produce a group of rank that's greater than k minus 1. And that's the moral of this story here. Okay, so free groups we touched on. So this is the definition, right? So really the good way to think about them again is just the free group on 2 letters, right? So I have, free group, 2 letters, so I have my generators A and B. All right, so the elements of the free group are just words in the alphabet A, B, union, A inverse, B inverse, okay? And so anyway, the free group is really kind of a base, even though it's not necessarily taught this way, it's kind of the most basic kind of group. It's also very hard to deal with because it has no relations. Okay, so there are no relations in a free group, and we call the elements words. Okay, so a reminder about our definition of K-free, groups K-free for every finally generated subgroup, of rank less than K is free. The point of this slide is to let you know, in case you were wondering, well, how do we deduce K-freeness and how common is it? And is it a weird condition to have on my fundamental group? And the answer is it's actually, if you want to say, it's common in the following way, okay? So if we have a closed orientable hyperbolic 3-manifold, Jocko and Shalen showed that if K is 2, then we have this dichotomy where either the fundamental group is 2 free or admits a finite cover where the rank of the fundamental group of the finite cover is 2. So I'm either 2 free or something else that's easy to deal with. Okay, and same thing when K is greater than or equal to 3, color Shalen showed, modulo some small requirement on the first homology groups, on the dimension of them, and you can think about the first homology group as the abelianization of the fundamental group, just to make things kind of logical here. So modulo some condition, then for k greater than or equal to 3, the fundamental group is either k-free or something else. And the something else there is that it then, if it's not k-free, it contains a closed incompressible surface of genus less than or equal to k minus 1. Okay. All right, so quantitative Mostow rigidity theorems on volume and k-freeness. What we're going to look now, remember the idea was, hey, how can we take this info, this restriction on pi 1 of m, it's a bridge, right? Like using k-freeness to kind of say something about volume. And we know volume of m is a topological invariant for Mostow rigidity. So the point of this compilation is to show you how that if you have some information about pi 1 of m being whatever free, 2 free, 3 free, 4 free, 5 free, that you can see there's a pattern here that we're able then to extract information about maybe about a point of m, or in the rank 3 theorem at the very bottom, like a certain subgroup of gamma. But the moral of the story is that we're able then to do something about volume. We can, for pi 1 of m is this free, then we're able to get a lower bound on volume. And if it's not, then otherwise we're able to say something, let's say in the case you see here for 3 free and 4 free and 5 free, that the result is that, well, if it's not true, if the volume is smaller than something, then the dimension, homology groups are abelian and they're vector spaces. The dimension of the first homology group with Z2 coefficients of them is less than or equal to something. Okay, and all that's to say is that, well, the topological complexity, if the volume is small, the topological complexity in some sense cannot be too big. Okay, small volume, topological complexity also kind of small. Okay, all right, and I want to point out in the first bullet here that we use as our example in the log 2k minus 1 theorem is sort of the k equals 2 case. Remember, we had two isometries, xc1, xc2, and we said, hey, it's always true for any pair of isometries. So given a point in hyperbolic space, that one of them's got to move that point by a distance at least log 3. And so when you think about that, that's what's going on upstairs in the hyperbolic space, how the group is acting on hyperbolic space. Well, remember, to get our manifold, we quotient out by that action, which means we identify the point and where the isometry takes it, which is at least log 3 away. And so in the manifold, that turns into what you see here is its bowl of an embedded bowl of radius log 3 over 2 and m. And that's Jocko and Shalen show that in the 2 free case, and 4 free, 5 free, and the rank theorem at the bottom, that's a collaboration between me and Peter Shalen. And in the 4 free case, it improved on work of Color Shalen. Previously, the minimum volume bound was 3.44. Okay, so these are the formal statements of those theorems. The 5 free theorem really subsumes the rank theorem, but the rank theorem is left there because you can kind of see it is kind of a generalization of some of the earlier ones, except the results, the conclusion, we get something that's a little bit harder to deal with and extract geometric information from. And it says something about the subgroup. It says something about, the fact that the rank of every subgroup of the group that's generated by elements of the isometry group that move a certain point, distance less than log 2k minus 1, that, well, all of the subgroups of that group can't be, every one of them has to have a rank that's bounded. It's kind of hard to extract, though, geometric information there, so still working on that one. But the 5 free result was an improvement. Okay, this is the no $3 million slide. Ian Eagle, winner of the Breakthrough Prize, remember earlier in the talk, has a result with Leininger and Margalit involving the dimension of the first homology group. So it's a linear bound involving volume. Okay, and so together with Peter Shalen, we were able to improve that linear bound. So you can see there, so 334, and we improved it to 168. There's still more work to do. but the proof was really interesting and cool. And while we used some of the techniques of Agel, Leininger, and Margulis to start off, we ended up doing a whole bunch of different stuff. And by different, I mean even including an application of the four-color theorem, which is really cool and a sort of a bucket list thing. So that's really great. Now, lots of different areas of math come together here. We didn't really talk about combinatorics too much, or graph theory, and those ingredients are used in the rank theorem. There's other things here used in some of the other results. And so there's no proof in this talk. So for the hyperbolically curious, I have some slides after the talk. This one at least is worth looking at. Nerves are cool. In case you want to piece together some elements of a proof for the ring theorem. So thank you so much for your time, and I look forward to chatting with you. And by the way, the places you'll go, that really looks like a one-cusped hyperbolic two-manifold to me. I don't know about you. So thanks again.